Okay. Guys, I'm just going to remind you today, it's Aria who's going to talk about, I should say, Hudgkin Huxley model of the brain. I'm sure she has done a great job, and most of you has already presented your work about Hudgkin Huxley model of the brain, which is a kind of, I should say, a very important, I should say, a chapter in the computational neuroscience. If you are interested in that field, this is computational neuroscience, the discipline that you try to use mathematical, I should say, functions, which you're learning it now with the advanced function tool, and a little more advanced, particularly just applying, I should say, differential equations to describe the math, the brain, the function of the brain, and the neural functions. Then now I think, Aria, are you ready now?
Teacher, can you hear me?
Yes, I can hear you.
Okay.
Aria, is it you 24442? Is it you 24442?
Yes.
Okay. Yeah. If you want, you can share your screen. And yeah, please go on.
Okay. How to?
You know how to share your screen?
I know how to, but
Yeah,
I don't
just
know.
check your ribbon below. It's take your cursor, take your mouse cursor below your screen. There is a red button, not red, green button. This is called share screen. Did you find it?
Yes.
Click on it. Ah, there you are.
Yes, thank you.
Fantastic, fantastic.
Okay. Can I start?
Yes, yes, please.
Hi everyone. Today I will talk about the Hudgkin Huxley model and can you see that?
Yeah, sure. We see everything.
Okay. So the first part, I will introduce how does our brain work. Our brains work like a big computer. Brain is composed of the cerebellum and the cerebellum and the brainstem. The brain receives information through our five senses: sight, smell, touch, taste, and hearing, and often many at one time. Brain tissue is made up about 100 billion nerve cells, and neurons are electrically excitable cells in the nervous system that function to process and transmit information. And
Sorry, Arya, can you go back to previous slide, please? Sorry about that. Thanks. Interesting. Very good. Thanks.
next part is there are two pictures that shows the Hudgkin, and the left one is Hudgkin and the right one is Huxley. They discoveries concerning the ionic maximum involved in excitation and inhibition in the periphery and the central portions of the nerve cell membranes. And can I go to the next one?
Yes, please, please.
Okay. And the Hudgkin Huxley model is a mathematical model that describes how action potentials in neurons are in, initiated and propagated. It is a set of nonlinear differential equations that approximate the electro characteristics of ex, exert, excitable cells such as neurons and cardiac
Myocytes.
myocytes. Yes,
Okay.
it is a continuous time in dynamic system, and Hudgkin Huxley model represents the biophysical characteristic of cell membranes. It could be simulated as electro circuit as the picture below is this picture.
Don't go to the next slide, please. Hold on a second, please. Okay, and now you have, what else do you have? You have the lipid bilayer, it has a capacitance.
Sorry, teacher.
Yes, Aria.
Um, um, so I can't to the next page now, right?
Oh, give me 1 second. Give me
Okay,
one
okay.
second. Thanks.
Okay.
Thank you. CM. GN represents what? Leak voltage gated and leak ion channels. What is GL? GL is linear conductance, huh?
Yes.
Conductance, electromagnetic gradients driving the flow by the barrier. What is that? The electrochemical gradients. Guys, I want to ask you a question from everyone. What do you understand from that fact that the electrochemical gradients driving the flow of ions are represented by the batteries E, and ion pumps as exchanges are presented by the current I? What do you understand, guys, from this phrase, the electrochemical gradients? Any ideas? Mingji, Oliver, David, Aria, Linda.
Teacher, you mean the batteries E?
No, I mean there is a phrase there. You said that the electrochemical gradients. What does it mean, gradients?
Gradients.
I mean, it's very interesting, guys. In this context, it means that when we talk about the gradients, you're going to see that more when you go to when you go to your calculus class, then after you take more advanced courses, it becomes vector calculus, and you will see that, for example, when there is, for example, imagine your pockets, huh? In your pockets where you hold your money. For example, on your right pocket, you have $50, $50 change, $1, $2, all goes to $50. And your left pocket, you have, let's say, you have $0, huh? That's, you see that there is a difference between the money which you have from your right pocket to your left pocket. And this difference in terms of the money, it is called the gradient. Gradient, it's a mathematical approach. You're gonna see that in vector calculus, which is one course advanced above your calculus class. When you talk about the gradients, normally, for example, the example which I told you, it was about, for example, the money which you have in your pocket. But in terms of the Hudgkin Huxley model, it means that, for example, outside cell has, for example, more chemical components, for example, like the sodium compared to inside cell. Then you see that when you have two different areas, in physical areas, point x1 and point x2, it can be represented by outside of the cell and inside of the cell, when the concentration of one chemical substance, like the sodium, on one side of the cell is bigger than the other side, which it causes the flow of the sodium from outside to inside. That's what they call that electrochemical gradients. And you learn about the word gradients, you're going to talk about that as an operator in your calculus class. The gradients, this is called a part of the vector calculus. You can develop some mathematical operations and tools in order to study how the gradients just flow, I should say, in the space. And that's, I just wanted to share that with you all. Yeah, thanks, Aria. Please go on.
And the next page is the basic components, and the typical Hudgkin Huxley model treats each component of an acceptable cell as an electric element. Current flowing through the lipid bilayer is written as this formula.
So what that formula represents?
Percent is the current flowing through the lipid bilayer is written.
I'll give you 1 second. Okay, it's okay, thanks. Yeah, please next slide. Thanks.
So teacher, you want me to?
Yeah, move on. Go to the next slide. Thanks, Aria. Thank you.
Because I don't know how to do the formula like this, so I just want to explain that.
That's right. And no worries. These are differential equations, and I just wanted the students to take a look and see what is dV by dt, which essentially we have a session before we finish this course. We are gonna talk about introduction to the calculus, and it makes you ready for your next class, which is going to be the calculus. We're going to see this stuff maybe in the next week. But so far, it was good that you see this stuff, that it prepares your mind for the next step then.
Okay, and next is current through a given ion channel is the product, and this formula I the equal G AM minus VI, and VI is the residual potential of the ion channel, and that's for cell with sodium and potassium channels. That the total current through the membrane is given by this formula.
Interesting, interesting, awesome. Aria, in the next week, move forwards, you're going to see the significance of equations like that and what do they mean and why do we need them in the math and what do they represent and what is the purpose of introducing these kind of notations in our equation. You're going to see them next week.
Okay, we
Thanks.
will learn this.
That's right.
Okay.
And it makes you prepared for your calculus class next term. I don't know if you're going to take that in the summer or next fall, then, but it's a good thing that you are getting prepared for it then.
Okay.
Yes.
And the next page is the next part is voltage gated ion channels. And so using a series of voltage clamp experiments and by varying extract cellular sodium and potassium concentrations, Hudgkin and Huxley developed a model in which the perpetuates of an acceptable cell are described by a set of four ordinary differential equations. So the M is controls NA channel opening, and the H controls NA channel closing, and N is controls K channel opening in those formula. Like the right graph. So for each value of the membrane's potential, that the non-linear gating equations reduce to equations of the form. You can see the equation below.
Very nice. Very nice. And guys, one other thing I just wanted to mention, look at that. In this Hudgkin Huxley model, as you can see, and most of you has done the research, and also Mingje, Oliver, and Sean. And you will see that, for example, and also right now, sorry, the Aria, you will see that, for example, the sets of the equation which you have, the upper box, which, for example, you have the notation dVm with dt.
Yes.
These kind of equations, that's right, they are called differential equations. And you see that you can represent the dynamics of a neuron from the time the action potential starts to convey the information along the axons. It's represented by these sets of nonlinear ordinary differential equations or linear differential equations. But what is a differential equation? It's going to be the topic that you are going to see that on the first or second year of your university, depending on what major you choose. It's essentially, as you see, that's an equation which involves the derivative or the rate of change. For example, Aria
Mm-hmm.
and everyone in the class, look at the first question which Aria has written, it's written M as an index controls sodium channel opening, and you will see that the equation involves a term after Cm as dVm over dt. D over dt, what does it mean? Vm, you see Vm. Aria, what was Vm? The voltage of membrane, huh?
Mm.
That's right. Look at
Okay.
that. What does it mean? dVm over dt, it's an operator which describes the change of the voltage across the membrane with respect to the time. dt, t is the time. It means that d over dt, for example, you can change d of your money inside your pocket with respect to the time. It means that the rate that the money which you have in your pockets is going to change. For example, every hour you put $1,000 in your pocket, then it means that the d of your money over the time, it becomes 1,000. It shows that how things are changing. Then effectively, if things are constant and if they do not change, then you see that the rate of change is going to be zero. Then essentially, dVm over dt, it tells you how the voltage across the membrane of a neuron with changes of the time is going to change itself. And an equation which involves these kind of operators, they are called differential equations, which is a fast and huge topics in the advanced math in the university. But at this stage, it is very, I should say, commendable. And I have to clap my hands for you that now you can just see these equations and see the significance that what is the importance of these ones. Yes, thanks, Sorry, I've talked too much. Please go on.
Okay. Mhm.
Yeah, Arya, please move on.
Okay. And
Thanks.
so the next page. And is the voltage gated ion channels also. So for every value of membranes potential Vm, the sodium and the potassium current can be described by the following equations. It is equations.
That's right.
And the voltage of membranes, we show the time graph is this graph.
Oh, fantastic. Fantastic. I really like these graphs. Do you know what are these graphs, Arya? Do you want to talk about them? What do they
Um,
show?
this graph.
That's right.
I um, I didn't pay much attention on this graph, so
Uh, no worries. It, it's essentially, this is very interesting. Look at this graph. It shows that how the neurons, they fire, they call that the fire. For example, when you feel something, when you have some kind of senses, when you want to think, the neurons in your brain, they, because of, I should say, the changes of the ions from the intercellular to extracellular, they change. They, as a result, that what you call that in your graphs, in whatever you did so far, the research, this is called action potential, the voltage difference. And when it reaches to a threshold, to a minimum level, they call that the neuron fires. And you see that the voltage on the y-axis goes all the way up to almost 110 millivolt within a couple of nanoseconds. Then it goes back all the way down there below zero, which is a kind of, it says that, okay, the concentration of the ions again, they are just reversed. This is called, and you see these ones, for example, you showed two of these reds, they call that spikes, these plots. You showed them too, but they are continuous. You can see the many of them, and they call that the firing pattern of a neuron. when it's activated. And that's a very impressive work of this model. Then it predicts the firing pattern of the neuron as based on the models. Then yes, thanks, Aria. Thanks. Please
Thank
go on.
you. And the last part is the Hudgkin Huxley model is regarded as one of the great achievements of 20th century biophysics. So nevertheless, modern Hudgkin Huxley tape models have been extended in several important ways. There are three parts. And wait a moment.
Are you
And
done?
the first one is the stochastic models of ion channel behavior, um, um, leading to um, stochastic hybrid systems. And the next one is additional ion and channel populations have been incorporated based on experimental data. And the last one is the models often incorporate highly complex and geometries of and then dressed and uh, and axons often based on max um, max
Give me 1 second.
based on max scope data.
Are you done?
Yes, this page is done.
Okay, thanks. I have one question for you.
Yes, teacher.
Just on the third part, you have said that models often incorporate highly complex geometries of dendrites and axons, often based on microscopic data. Where did you, I'm so interested to study on that myself, continue further, because I learned that from you right now here. From where source did you get that thing? I'm very interested to see how the microscopic data is incorporated into the Hudgkin Huxley model. Do you have any source for the line, paragraph number 3, which you have written?
Can you speak again?
From where did you get that information, part number 3? Can you just send it to me?
Okay. The link, right?
That's right, because
Okay.
this is part of my research. I want to just also get an access to that because it's interesting how the complex geometries of the
The
dendrites.
you mean the third one or the second one?
Oh, no, third one.
Okay, I will send you the link.
Anytime, today or tomorrow. There is no rush.
Today I can give you, teacher.
Oh,
Let me
fantastic.
find.
No worries. Anytime before the today ends. And the very last question for you and for everyone. Guys, do you know what does it mean, stochastic model? Arya, don't want to go
Yeah.
yourself first?
Oh, what, teacher? Sorry.
Stochastic models.
Stochastic. Oh, sto teacher, I send the link to your email
Oh, you
or
sent it right now?
um uh, because I'm funding and
Yeah,
I,
email is fine. Email is totally fine.
okay.
Thanks. Guys, what does it mean, stochastic models? Any idea from anyone?
No, teacher.
Hmm? Sean, Mingji, Oliver, Linda, David,
No.
no one? Sean, you have no idea? Okay, guys, it's a very interesting thing. Mingji, how about you?
I have no idea.
Okay, guys,
So
look at that. Yes,
it means random.
that's so true. That's so true. Thanks a lot, Aria. Thanks a lot. Guys, what does it mean? Essentially, in the mathematics, you have two broad method for modeling a natural phenomena. One of them is deterministic. Deterministic means that the model, which it gives you a very precise prediction of what's going to happen next. For example, imagine that. Every day you walk from your home to the school, huh? Every day without exception. Then this becomes a kind of a deterministic way. Because it's easy for me to predict accurately what's going to happen tomorrow for you. Tomorrow, again, you're going to walk from your home to the school, and it becomes a kind of a deterministic pattern and model of your life. But stochastic model is exactly the opposite side. Stochastic model in the math, it means that, for example, you imagine that you do not walk every day from home to school. Your plan maybe is that they go to school, but tomorrow you go to the cinema, the next day you go to the swimming pool, the other day you just go to, let's say, the gym. And it's not easy to predict tomorrow, where are you going to walk or where are you going to be? It means that there is a randomness. It's a random model, which prediction is not going to be easy. And if you're interested in the finance, then in the finance, you're going to work a lot with that. You have stochastic model to predict the stock price, let's say, for example, in future. And that's what it means, stochastic versus deterministic. Yeah, thanks. Aria, anything else to add?
Hmm?
Anything else you want to add?
No, that's all. Thank you.
Awesome. Good. Thank you very much, Aria. It was a great presentation, and I really enjoyed that. Thanks.
Thank
Thanks a
you.
lot. Guys, any questions for Aria? If any questions you have for Aria? It seems that nobody has question. I asked my question. Then please, Aria, send
The link,
the link.
please.
That's right. Anytime today. There is no rush.
I will do this.
Awesome.
I will send to you today because
Thanks a
I'm
lot, Aria.
banned.
Oh, awesome. Thanks a lot. Much appreciated. Then if you don't mind, I just stop sharing, huh? Your slide,
Okay,
huh?
okay. Teacher,
Okay.
do you want other link
No,
about
just that one is okay. Number 3.
number 3? Okay.
I'm very interested to see how the microscopic data about, let's say, about the geometries of the axon and dendrites can fit into the model, because I haven't done that myself. I want to do that myself. Then that's the homework for me.
And because I search a lot
Oh,
for this
thanks.
question.
Oh, awesome. Thanks. Then it's going to be my homework, then how to fit the data into the Hudgkin Huxley model, then the data from the microscopy of the geometries of the axon and dendrites.
Okay,
Awesome. Thanks a lot, Aria. Much appreciated for your work. Thank you.
teacher. And I'm stop the share.
Okay, I did it.
Sharing.
Thanks. Okay,
It's okay.
and now